Module 5 is the second module for tension members. Lesson 10 covers the evaluation and design of tension members. Tension members are designed for three possible limit states or failure modes. They include gross section yielding, or GSY, net section rupture, or NSR, and block shear rupture, or BSR. As we will see, all tension members must be checked for gross section yielding and net section rupture. Bolted connections for rolled shapes usually have to be also checked for block shear rupture. The smallest calculated strength from these two or three limit states is then the member's design strength. In design, where the member must be sized for a given load combination, the initial selection is based on gross section yielding, and then once the shape is selected, the other limit states are checked. Note, the majority of the design provisions for tension members are located in Chapter D of the AISC specification, which is Part 16 of the Steel Manual. Block shear rupture provisions, however, are located in Chapter J of Part 16 and will be discussed in Lesson 11, which is the second lesson of Module 5. Gross section yielding controls the design of a tension member along its length. The limit state is defined by the yield strength of the steel times the gross area of the member. A reduction factor of 0.90 is used to adjust the nominal strength to the design strength. This is equation D2-1 in Chapter D of Part 16. The stress is limited to the yield strength since, as the member yields, the member will begin to stretch uncontrollably along its length. The member would not be able to elongate enough to raise the stress to the ultimate or tensile stress, let alone strain hardening. Think back to the typical stress-strain curve of Lesson 5, Module 3. Understanding why the ultimate stress cannot be used for the gross section of the tension member may be useful on an exam. It's kind of like a hint. At the end connections of tension members, the stress will concentrate and the deformation or strain can occur over a shorter length. Therefore, the local stresses can reach the tensile strength of the steel. Failure at the connection location is defined by net section rupture, which is defined by the tensile or ultimate strength times the effective area. This is equation D2-2 in Chapter D of Part 16. Remember, the effective area is the shear lag factor times the net area for a bolted connection and is equation D3.1 in Chapter D of Part 16, while for a welded connection, it is U times the gross area. A reduction factor of 0.75 is used to arrive at the design strength. Note that the reduction factor is lower for net section rupture than gross section yielding, recognizing the increase in uncertainty in the design of connections. More things can go wrong in a connection than along the length of the member. For bolted connections, rupture or fracture will only occur through the lead bolts. This is the location of maximum force in the member and allows physical separation of the member from the connection. Rupture through any other path is not possible since the member force is lower, the elongation required for rupture is prevented, and the member is unable to separate from the connection. Shown is a channel shape bolted to a gusset plate. The rupture path must occur at the lead set of holes, as this is where the highest force is in the member and allows the member to physically separate from the connection. Also, when calculating the net area, only 2 bolt holes are deducted from the gross cross-sectional area of the member since only 2 bolt holes will be in the rupture path. In addition to designing for the two limit states of gross section yielding, net section rupture, the slenderness of a member must be checked. If a tension member is too slender, it is prone to damage during handling, fabrication, transportation, and/or erection. Also in service, it may have excessive deflection and be susceptible to vibration while in service. To prevent these problems, the member slenderness, as defined as its length divided by its least radius of gyration, should not exceed 300. Watch your units with this calculation. While a ratio, the length must be in inches since the radius gyration is always given in the section table in inches. Note that most rolled shapes have a radius gyration of both axes, x and y. However, the minimum radius of gyration of a single angle is actually about the z-axis. Section properties for the z-axis are of single angles, including the radius of gyration, are given in Table 1-7. Think of this provision as a serviceability limit state. There are two types of problems: analysis of a given member for its maximum strength where the shape size is given, and then there is the design of the member where the required design load is given and a suitable member size must be selected. An analysis problem is rather straightforward, as all you do is calculate the strengths from the applicable limit states, say gross section yielding, net section, fraction. The smaller the two strengths controls, then the design of the member. The design problem is a little more complicated, as you don't have a member size or dimensions, nor the cross-sectional areas. That is what you're trying to determine. Therefore, you don't know which limit state controls. In the design process, the required member strength is given or the service loads are given, and you must apply the load combinations to find the controlling factored load combination. The design process for a tension member usually starts by assuming that the gross section yielding controls the design. This is because the equation for gross section yielding can be easily rearranged and solve for the one unknown, which is the gross area. The cross sections of the shapes are arranged according to their weight, which directly corresponds to the cross-sectional or gross area. Once the member size is selected, the net section rupture is calculated. If the calculated design strength exceeds the required strength, then the selected member size is adequate. If a lower, new, heavier shape size must be used, that'll be indicative of having a design strength lower than the required design strength. How much heavier you need to go depends upon how much strength is needed to satisfy the design. The design process can therefore be iterative. Experience has shown that, in general, the design strength of members made of A36 steel will be controlled by gross section yielding, while the design strength of a member made of a grade 50 steel may be controlled by net section rupture. Regardless of the steel type, make your initial selection based on gross section yielding. Even if net section rupture controls, you'll be in the ballpark with your initial selection based on gross section yielding, and you should quickly arrive at a suitable design. This ends Lesson 10.